Swayam Prabha. Digital India. Educated India.
This response of a linear system to a sinusoid, being a sinusoid of the same frequency, makes it very convenient in many ways. First of all, for analysis, and later in some other course you will see that any signal can be decomposed with sum of sinusoids. So this is not even all that limiting. Although you characterize it only with sinusoids, you can find the response to any other input also. It's a little more painful in that there's a little more labor involved, but you can still do that. Okay, and also for testing. Okay, so what is testing after all? When you want to test something, let's say you have some standard input and you have the calculated output for the standard input. Okay, it can be anything. When you do the experiment, you apply the same standard input, measure the output and see whether it matches with what you calculated. That's the essence of testing, right? You have something you expected and something you test to see whether you get what you expected. Now the problem is that if you use some other input, then there can be other features in the system that can manipulate the signal. That is, let's say this itself is the circuit I want to characterize. Okay, this is the input and this is the output. And to do this, I'll apply some from a signal generator, some input to that. Okay, and then I'll take this to an oscilloscope. And measure what comes out. Okay. Now I can use any input, right? For instance, I could try using a square wave. You can first of all surely calculate the response of this to a square wave. But of course, it's slightly involved, but you can calculate it. It will turn out to be something like that. Okay. Some piecewise exponential stuff. For piecewise constant, you will get piecewise exponentials. Now there are many problems here. First of all, calculation is slightly more complicated. Top of it, you have to measure this precisely to see whether you are getting what you are expecting. And more importantly, there will be other stuff here that will disturb the actual input. I mean, you have wires going from here to there. Okay, a very simple model for this is, let's say this itself has some resistance and some capacitance. So what gets applied to the input is not even a square wave. That itself is some sort of exponential. Okay, so you have to measure this very, very precisely, calculate the output for that, and then match the measured output to that one. So this whole thing is a pain. Now if you have a sinusoid, what happens? This also is a linear circuit. So what you get here is also a sinusoid. Okay, it may not have the same amplitude as this one, but that's okay. Let's say I want 1 volt here. I'll actually measure it. Maybe I'll have to set this to 1.1 volt. That's all. Okay. So I can just manipulate this. I'll get a sinusoid here. I'll also get a sinusoid here. And all I have to do is to measure its amplitude and phase. Okay, that's also not very difficult to do. So let's say I have 2 channels of the scope. I can measure the amplitude. And also, let's say I plot both simultaneously. I can also measure the phase by looking at this time difference. Okay, so now because these exponentials, complex exponentials or sinusoids are eigenvectors of linear systems, this is very easy. Okay, now I took this test circuit itself as an RC circuit, but that's not necessary. This could be anything. I mean, typically amplifiers are tested like this. You measure amplifiers with sinusoidal inputs, and let's say it's an audio amplifier, you have some range of interest like 20 hertz to 20 kilohertz. You have sinusoids of different frequencies, measure the response and see how it behaves. Okay. So if you see amplifier data sheets, they will give you the frequency response. Okay. Could we use exponentials? That is exponential ST with a real S. Okay. If you have exponential ST, that's a general exponential. You can have real S, which means that you have waveforms like this if S is negative, or like that if S is positive, and S is purely imaginary. It's a sinusoid with a constant amplitude. And if S is complex and the real part is negative, you get that. the real part is positive, you get that. Okay. So now I think your question is, why should we not use S real? Okay, what's the problem with doing that? Could we do that? That also satisfies this property, right? I mean, it goes through a linear system and then comes back as the same exponential. What is the issue? Is there an issue? The problem is that it's not a persistent input. Okay, that is, it is of course true that the response to an exponential is an exponential, but you apply an input and then after some time it decays off. Okay, so that could be slightly longer or shorter, but it will eventually decay. Whereas the sinusoid is a persistent input, so it's a lot easier to use the sinusoid. And also, we are measuring the steady state response, right? So what it means is that the sinusoidal steady state response, you apply a sinusoid. It's not that immediately you get a sinusoid as the output. At the beginning, it will have the exponentials also, which are part of the natural response of the system. But for any stable system, the natural response parts will die out and the force response will stay. Okay. Now, for an exponential input, what happens is the natural response will die out, but the force response also dies out simply because of the nature of the input. Whereas for a sinusoid, the natural response of course dies out, but the force response part is persistent. Okay, so the response to sinusoid, let's say your time constant is 1 microsecond. So you apply a sinusoid, maybe the natural response lasts a few microseconds. So you look at the output after, let's say, 100 microseconds to be safe. The natural response is gone, you will have only the force response. It's very easy. So that's why you use sinusoidal inputs, not exponentials.